Today I'm going to work through a little exercise I find I keep forgetting the explicit form of Lorentz boosts. Although it's uh, easy enough to know that the form is going to be something like the original t times something plus the original x times something, and a similar structure for the x prime. Uh, the actual factors that go into it frequently I forget. So this isn't meant to be pedagogical. It's just an exercise for me. Um, and one thing, let's see if I can remember some of the finer details. Uh, as opposed to Galilean transformations, where you have something like an x vector being sent to an x vector minus a velocity times a time. Uh, those are the Galilean type transformations. We're going to look at Lorentz transformations, and instead of being like an orthogonal group in 3 dimensions, we're going to be looking at something in 4 dimensions, or more specifically, 1 time dimension, 3 spatial dimensions, and it's going to be some sort of Lorentz transformation matrix times the original vector. If you want to consider all linear transformations on your initial vectors, you could also add on a little translation, but we're not considering the full Poincaré group right now. Excuse me. We're just interested in finding an explicit form. Yeah, let's work through some identities. Let's see if we can. The group, orthogonal group in 4D space-time is going to look like a union of Lorentz transformations with a positive determinant, with Lorentz transformations with a negative determinant, along with Lorentz transformations with positive, I believe it's positive, it's either positive or greater than 1. And similarly for Lorentz transformations with a 0, element that's either negative or -1, one of those. That's what the splitting up looks like. Oh, sorry, that is positive. That is determinant is negative. What we care about is the proper orthochronous Lorentz group, which is something like this is positive or greater than 1. I can't remember which. And we have a positive determinant. I can't remember if it equals 1, but it's certainly positive. And we're going to consider infinitesimal Lorentz transformations in this at first, because the nice thing about the orthochronous Lorentz group is that orthochronous proper, I think proper is usually first. Proper orthochronous Lorentz group is you can have infinitesimal transformations within it that take you through the entire group, while the other groups don't let you cover their full expanse with just infinitesimal transformations. Let's remind, what is an infinitesimal transformation? Well, in this context, it's going to be something like transformation is going to be something that strays a bit from the identity. So that plus a little deviation, little lambda. We want to figure out some properties of little lambda so that we can later take the exponential map and recover a finite Lorentz transformation. First, the thing we care about that Lorentz transformations preserve is the metric, the space-time interval. So let's use a differential version. It's going to be your metric times your little differential forms, or let's not think too rigorously today, times your little dx's. In this case, we're just going to consider Minkowski space-time. So we're going to use a Minkowski metric, dx mu, and this matrix in our, let's do mostly pluses signature. It's going to look something like -1, 1, 1, 1, with the zeros off the diagonals. So that means we end up with a space-time interval of minus dt squared plus all of your remaining spatial distances squared. And I'm going to use x1, x2, x3 because I don't want to use x, y, z. Excellent. Now from here, we know that the space-time, well, we insist, sorry, that the space-time interval before and after we take a Lorentz transformation of our vector, for vector, it should be unchanged. This is supposed to be a little prime. Maybe I'll use a squiggle. We insist it's the same. So that means we're going to say our original ds squared, that was still this guy. And our final one is going to be, we have the same metric before and after, but it's going to be on the changed intervals, not changed little dx's. Now we know what those little dx's look like. And actually, to make our notation better, I'm going to call that alpha beta. So we're going to have eta, our metric, and the primed coordinate, that's really going to be our Lorentz transformation on the unprimed. So it's going to be alpha, maybe we'll call that mu x mu times our Lorentz transformation on the original again. Do bada bing, bada boom. Now all of these are tensors, but we're keeping things in index notation. So, and we're using Einstein summation convention, of course. So this multiplies, that is summed. So we have alpha 0 x 0 plus alpha 1 x 1, and so on. The point is I want to group the x's outside, so it'll look kind of like our left-hand side here. And why am I doing this? Well, I want some sort of relation with my Lorentz transformations in the metric, or just some sort of relationship that I can exploit to find more properties of the infinitesimal translations. So get that guy, alpha mu, beta nu, x mu, x nu. And remember, we're insisting that that is the same thing as the original ds. This is supposed to be true for any translation. Oh, apologies, these are infinitesimal. For any such infinitesimal translations. So we can factor them, and we end up with the metric we insist is the same thing as our Lorentz transformation multiplying on the left with the metric, and it multiplying on the right with the metric. Oh. Now I think there's a subtle point about the transpose of a Lorentz transformation coming up here. Highly recommend Sean Carroll's book for general relativity, but he talks a bit more about that. I know we want to end up with an equation that looks something like this in matrices. Our transpose of the Lorentz transformation times our metric times that guy. Oh, yeah, you can sort of see what's happening. This is kind of standard matrix multiplication going on. But here, see, something a little funky is going on, where it's not the closest index that's getting multiplied. Like if we had something that was like this instead, this would be a little more something we're more used to, but it's not. So that's where we can make a subtle definition that lets us get this sort of equation going on. But moving on from remembering that, remember, this is just a little exercise for me. Okay. You guys know how to do this? Okay. Oh, okay. We've got this equation. That's a general equation. That's true for any Lorentz transformation. Now let's deduce something about infinitesimal translations from it. So let's rewrite it in terms of the infinitesimal translations. I'm going to just say that's an equality. And that first one is going to be an infinitesimal translation. So here's our infinitesimal translation. And then here's our metric. And here's another infinitesimal translation. Sorry, transformation. I'll say a lot of wrong words here. Okay. Now, let's assume that any Lorentz transformation can be expanded in a power series, which I believe is the case for Lorentz transformations in the proper orthochronous group. So we're neglecting terms in general for order lambda squared type of deal. So we're going to be neglecting such terms in our consideration. So let's multiply this side first. We're going to have mu beta going on, and that's still multiplying that guy. That's from the first direct delta acting on the metric. And then we're going to add on this guy acting on the rest. Now, notice for the right-hand term here, if I multiply in this guy, I get it against direct delta, which is all fine. But here I get an order 2. I get an order lambda squared. So I will ignore that because lambda is small. Hunky dory. So let's do some more routine calculations. Direct delta there. Okay, we get our original metric, and we'll define. We want to figure out how we can multiply this by this. So let's say define this as the usual lowering scheme. Yeah, so it's just the usual way of lowering indices. That's what we're going to define this symbol by. Now, these two multiplied together give us another metric. And that metric is going to be alpha mu. And then we have our order lambda squared that we ignore. Now this right here, similarly, is going to be mu nu instead. So rewriting our whole equation, we get a cancellation. And we find that our infinitesimal transformations are anti-symmetric in this lowered form. Epic. Actually, will give us quite a bit. Now, physically, what Lorentz transformations are possible? We just care about a boost, but let's just talk about them. How many physical ways are there? Well, there are 3 ways you can rotate 3-dimensional space, right? You got your x1, x2, x3 directions, so you can rotate space in those 3 ways. So you have 3 rotations. And then you can also boost in any of those directions, which is a type of rotation between the time and spatial coordinates. So you have 3 boosts. So that means we have a total of 6 Lorentz transformations, right? 6 degrees of freedom going on. How many degrees of freedom do we have in our infinitesimal translations? Well, it's going to be looking like a matrix, an anti-symmetric matrix with 16 components. Well, how many degrees of freedom does it have? If we consider a diagonal component, well, we know that has to equal its negative. So its diagonal is all zeros. And then this guy is going to be the negative of that guy. And this guy is a negative of that guy. And you're going to see a pattern. All of these are going to be negatives of what's going down here. So we just need to consider how many spots we have remaining here. We have 1, 2, 3, 4, 5, 6. So we have 6 degrees of freedom. And that is exactly what we physically expect. Very good. From here, very good. Okay. Yeah, now we can physically investigate what those different components mean. For example, we could consider a matrix that looks sort of like zeros there, component there, negative there, then zeros everywhere else. Yeah, I'll call it theta. Actually, no, let's call it phi. Well, this is mixing between the 1 and 0 components if it acts on 4 vector x mu. So that is a boost in x1 direction. Very good, that's what we want. Let's consider another one for fun. What about infinitesimal translation that looks sort of like, let's mix these two components. Those two components, well, that mixes 3, it mixes x3 and x2, so it's a rotation along the x1 axis. And you can find the remaining 2 rotations, remaining 2 boosts, the same kind of reasoning. But now, let's find an explicit form of a boost. Okay. Find the boost. Okay, our boost in the x1 direction, it's going to be the exponential map. So by that I mean, here's an example. Consider the 2D plane. Say you want to consider a translation from the origin, point A. That translation can be built up out of many small translations. If you make these translations infinitesimal, then you need to integrate over all those translations, and it's going to end up looking like an exponential. How does it end up looking like an exponential again? I think that would be helpful to think about. This gets into the Lorentz algebra versus the Lorentz group and Lie algebras and differential geometry stuff, which is all awesome. how does it go? It's because you integrate over translation. So you start at 0 and well, I guess let's think of it more discretely. It's going to look like adding a bunch of dx's. Well, that's going to end up equaling a total change of x kind of thing. Where's the exponential come in? Yeah, this is a pretty key part of the argument for, because I can do the matrix manipulations at the end, but it'd be nice if we can justify why are we considering something like exponential of our matrix. I want to justify that. Oh, okay. Okay. I think it's a little straightforward. I think it's something like we say our infinitesimal translation looks like, well, actually, let's say a general translation looks something like 1 plus a little bit plus a little bit. Expand it in a usual Taylor series kind of look. And you notice, oh, no, right here I'm already jumping to the exponential. And you argue for why it's exponential itself. Because here, you notice for the small lambda, we recover our approximation. There are other Taylor series that do the same thing. Why is this one special? Well, we're considering a product, 1 plus a tiny number, and we just keep multiplying it again and again. And actually, let's let phi be the small parameter. And this way, lambda equals something like phi times non-vanishing for a non-vanishing tensor, something like that. We can make phi go to 0 like 1 over n, for example, right? N is a natural number. And because, right here, we're stacking together a bunch of infinitesimal translations, in our case, we're not doing translations literally, we're doing transformations, stacking together a whole bunch of tiny boosts in the x1 direction. A single boost, we said, looks like this. This is our single infinitesimal boost, which will be this guy. And that's very good. Now, we don't know the form of this yet. We know the form of this. So let's rewrite it real quick. Uh, that is the same thing as raising that index, alpha mu, and then let's repeat that over here. We're going to have our metric and times that guy. Now this guy for x1 boost, we found it will look like 1, -1. Because before, we were considering different possible infinitesimal transformations. We found that there are anti-symmetric matrices or tensors, and that's how we found this form. So that's what that is. Very good, very good. Now if we're going to compose a whole bunch of these, roughly speaking, that's going to be a whole bunch of infinitesimal transformations n times, right? Because we're saying that this is like 1 over n. And look at this. You take the limit, n goes to infinity, and that's going to be the exponential of our generator there. Very good. Yeah, I believe this is called the generator. There might be some missing definition, including I in there. You see that in quantum mechanics. And I'm not going to worry about that. Not yet, unless it messes up my result. Okay. We're very close. Very close. So, our case, we want the exponential of, oh, we want this for a finite transformation. We need a parameter for how far the boost is going. I believe, let's use, what Greek letter do we like? Okay, let's use gamma as our parameter. That's just a real number. Gamma times our matrix there. And we want it to be in this kind of form, right? Well, that's the same thing as the exponential of gamma times eta. We want to raise that again. Very good, very good. And this is, of course, identity plus not identity. It's a power series, right? Oh, yeah, how do we multiply these out? done this in a matrix form before, but not in this kind of convoluted way. It'll be something like, let's write it out like this. Mu, nu, no, not nu, let's call that beta, times beta, nu, right? And then you continue that series. And let's write out the third term so we can get the pattern down. Ugh, hope you guys see where this is going. Maybe this is a dead end, and I should consider things from the lowered perspective. I could, yeah. Why don't I just consider, I could consider boosts like this, right? Yeah, okay. Let's scrap this way of doing it. Let's find the form of a boost like this. This is a finite boost, not infinitesimal. And that's going to be the exponential with our parameter of that. And this guy, we know the explicit form of. That's the 1 minus 1 on the x1 and x0 mixing components. So it will become nicely identity plus gamma times 1 minus 1 plus gamma squared over 2. And then it will be this matrix squared. Now let's evaluate this matrix squared. Notice that these components won't do anything. So it's going to look like this matrix multiplication. I'm no whiz at my multiplying of matrices, so I'm going to do it out nice and boring. Is that correct? I believe so. So that's what that is squared. And let's see what it is cubed. On which side do we multiply it? It doesn't matter because it's the same matrix, so it commutes with itself. Well, that's just the negative identity, so we get negative 1, 1. And we know that we're going to get this sort of alternating now. Okay. Let's consider some components of this, which will be easier. So if we consider the very bottom left component, that one is clearly going to be 1 plus 0 plus 0 plus 0 equals 1. And that's the same for the next diagonal over here. And we notice that the rest of the diagonal is also unaffected here. So that's the same thing for 1, 1, the same thing for 0, 0. Everything off the diagonal, except for the 1, 0, 0, 1, are going to be 0. So these are the only remaining non-zero components we need to worry about. Let's worry about the, what would it be? The 1, 0 component. That guy is going to look like 0 plus gamma plus gamma squared over 2 factorial and times a negative 1 plus gamma cubed over 3 factorial negative 1 plus gamma. I am, of course, looking at these components for this. This one will be plus 1. Oh yeah, sorry, I should write out the whole pattern of the powers of our generator. To the 1, we get the 1 minus 1. To the 2, we get our negative identity. To the 3, oh, this is getting messy. We get the negative of our original. 4, check this out, we just get the identity. And then finally, on 5, we end up back where we begun. So look at that. We know that act it on itself 4 times, you get the identity. Kind of like I to the 4th is 1. So we're going to get that kind of cycle. We're going to get plus, minus, minus, plus, and then it's going to be back where it started after every 4. And then plus gamma to the 5 or 5 factorial. And it's going to start looping. Now we want to find a power series that recreates some real function. Let's factor out gamma. So we have 1 plus gamma over 2 minus gamma over 2 plus gamma squared. That'll actually be a minus 3 factorial. Excuse me. 3rd, 4 factorial. And my postulate, my guess is going to be, this is going to be hyperbolic cosine or hyperbolic sine, because they mirror what's going on with sine and cosine rotations in 3 space. So they show up very nicely for rotations in 4 space. It's part of the reasoning of their names. And to confirm that, let's write out, let's find their power series. So let's say cosh of gamma, that's going to be the same thing as, well, actually, look at this. I'm not going to factor out gamma. This all, notice that this one, it equals 0 if our parameter equals 0. And I bet you that this one is going to equal 1 if gamma equals 0. Guess. And then here you're going to note that sinh of gamma equals 0. Sorry, sinh of 0 is 0. And also you note cosh 0 equals 1. So sorry, before I do the Taylor series, let's find the explicit form for this guy. So we're looking now at the 0, 1 component. Oh. I don't see any cosh showing up there. Oh. That's why my expansion is wrong. You see, I shouldn't be doing it with the generator. I should be doing it with with the whole infinitesimal transformation. This right here, that should really be something that looks like 1 plus little lambda. Or actually, let's call it 1 plus generator. Oh. I took a pause to look at my notes and from previous notes, and yeah, I'm about right. Except there's one finicky detail I haven't been able to establish. It should look like the form of an infinitesimal translation, except our infinitesimal parameter is actually now finite. Funny enough, right? Oh. Okay. Well, we were doing this for the lowered version. So let's throw out our work there because it is incorrect, but we learned a little mistake. This guy, well, that is going to be the same thing as this times the metric lowering the mu and for an infinitesimal transformation we know that this looked like alpha nu plus our parameter times our generator, because this whole thing was our little lambda. Well, multiplying it out, we get, I'll exploit the symmetry of the metric to move the mu to the left, and we get this guy. Very good. So our corrected statement should be this guy. And we're going to do this in matrix form. Now, the metric as a matrix looks like minus 1, 1, 1, 1 with zeros elsewhere. And for the particular boost we're considering, the x1 boost, the matrix looks like 1, minus 1, zeros everywhere else. Oh, excuse me. So writing this out as a matrix equation, we get minus 1, 1, 1. Actually, no, we get the identity first because we have this argument to the 0th power plus those guys. Well, it's going to be the metric plus phi times this guy. So we get minus 1, 1, 1, 1. And we get minus phi, phi. And again, let's write out our powers because this is still relevant to us. That gives us the identity. And then we get it to the 3, which equals the negative of itself. And then to the 4 will be the identity. After that, in a loop, we get that plus now the second power. So we're going to have diagonal elements going on as well. Okay, yeah, we're still recording. That's good. Yeah, maybe I'll start preparing for these. Doing an integral is much faster than trying to do out a problem in real time. Much less entertaining to do this. Much more fun to have the result flash in front of you, but this is for practice. Okay. So we're going to have minus 1 minus phi squared. Oh, no. That's not what we have at all. What we actually have here, we got to add these matrices and square them. Okay, so we don't care about this anymore. What we care about is when we square this whole matrix, which was the metric plus our little lambda, we care about squaring this whole matrix. This right here, when we square, remains unchanged. So what we really care about is what happens to this little matrix. Let's square that. I'll keep that there for a moment. All that is a lot of numbers. That'll be 1 minus phi squared plus phi, right? Yeah. Oh, we get a phi minus phi squared. We get minus phi, we get plus 1. So overall, this becomes 1 minus phi squared times the identity. And that is actually pretty slick, right? Because that makes a pattern easy to exploit. The third power, well, we know it's the first, so it's going to be 1 minus phi squared times our original little guy there. And as we continue, we'll, yeah, like for example, just to get more feel, to the fourth, well, it's squared, so we get this guy squared times the identity. Okay. Write this out a bit more explicitly now. One minus phi squared times identity plus, oh, actually, I can't factor that out completely. It does not go down there. And of course I should have a 1 over 2 factorial there, 1 over 3 factorial there. That'll be let's write that out. Negative 1 minus phi squared negative phi 1 minus phi squared phi 1 minus phi 1 minus phi squared 1 and so on. Now let's see if we can unpack the pattern. We know immediately what do we know immediately? I equals 0, I equals 0 if I equals 1, sorry, if equals 2, 3, ij equals 0 if I equals 2, 3. But we get a more interesting thing going on with the other diagonals, like the 3. Oh, that's right. So that's not right. Let's see. Ij equals 0 if I not equal j, but they're both in 2, 3. Off diagonals. The 3, 3, that looks like 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial equals 1 plus e. And that same thing with 2, 2. Not really the result I was expecting. That's telling me something's going wrong here. Okay, I think I found another issue. I think it was with my original notes. I just checked again, and I think this expression is a little misleading. I think I wanted to write it more like exp, more like this, plus exponential of that guy, because we want to do a whole bunch of these little transformations. And I hope that this will turn out to be an identity once I multiply things out. Let's see. If I want to raise the mu, so mu, nu, raise that up, that would give me the alpha nu. And if I do that same thing to this guy, that gives me very, very good, very good. So I'll be able to translate this. Okay, another error, more things learned. Okay, this makes more sense to me as well, because we expect that for this equal to 0, that this will equal, that for the parameter equal to 0, that this will just be the identity, because we're saying don't boost. And this form of the equation is easier for me to manipulate right now. Oh, but I'm going to have to transform it later. Maybe instead of doing out the power series now, and then transforming back into the mixed form, let's see if we can't turn this into mixed form ahead of time. So this, that's the same thing as, we know the form of this. We want to find the form of the other guy, of the mixed form. This is just the lowered form with a raised thing going on. And this is ordinary matrix multiplication here. So this is going to be minus 1, 1, 1, 1 with 1 minus 1. And that means overall we'll get 1, 1. Okay. So that means we can write our nice mixed form as, well, it's going to be the identity, as I briefly showed by multiplying this and raising an index. Will be that plus the exponential, I believe, the exponential of our mixed generator. We know the form of our mixed generator. Although it bothers me that I'm not seeing negative signs yet. It's fine. It will probably come down to a decision on which way you're boosting. So this will be matrix form identity plus oh, even this I don't like, because this is implying another identity. I'm confused. I'm gonna ignore that guy. I'm just gonna say I think this is the form we were supposed to have. So we get identity plus phi times our generator plus our generator squared. Now we want to consider algebra of this guy. So we square it and we get the identity. Very nice. So we're going to have plus phi squared identity plus phi cubed. And now we're back to where we started. And so on. So, okay, now things look how I expect them. 2, 2, 3, 3. They're both 1. We get most off diagonals being 0, except for the 4 by 4 or the 2 by 2 here. So let's look at the 0 component, right? 0, 1, 0, 0 is 1 plus phi plus phi, no, we don't get it, plus phi squared over 2 factorial plus phi to the 4th, 4 factorial plus, we only get the odd ones, equals sorry, we only get the even ones, my bad. Now let's try 1, 1. That guy, he'll get 1 plus 0 plus, it's the same deal. That's the same deal. That's very good because we want space and time to be on equal footing. Oh, not 0, 0, I meant. It's not 2, 2, I meant 0, 0. That puts space and time on equal footing. We also anticipate 0, 1 to equal 1, 0. Okay. This guy has no start, but it's phi. Yeah, we can already, by inspection, see that these are the same, as well as by physical grounds. So we get 0 plus phi plus phi cubed over 3 plus, okay, we only get the odd ones then. I guess we'll go like this. Now I expect sinh and cosh to show up, as I said. Sinh of phi, that is 1/2 e to phi minus e to negative phi. I expect it to show up here because you notice if phi is 0, these guys are 0, and these are 1 because of the 1 right here. So I'm kind of guessing that this is going to be cosh And this is going to be cinch, but we'll see. Okay, now let's find that Taylor series. It's going to be 1/2. The constant terms cancel. You end up with 2 phi plus. So the constants cancels, and then all the even powered terms, they'll cancel because negative phi squared will go like, it'll cancel the negative and they'll drop. So we'll have 2 of 3 factorial phi to the 3 plus da 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 da, which ends up equaling just the odd ones. And this guy will be just the sum. So we know odd terms will die. So we just get the even terms from the sum of the... I'm just finding the sum of their Taylor series instead of doing anything fancy. 2 from the constant terms, and then 2 phi squared over 2 factorial, and so on. Is even. Okay. So for a boost in x1 direction, I haven't said it was positive or negative. We can make that identification later. It's a simple argument, and this has gone long enough. Of rapidity, I can say plus or minus because I don't know which way. Phi. And just looking at space-time diagrams or doing some other basic manipulations with the space-time interval, you can find that the hyperbolic tangent of the rapidity is the velocity that you're doing the boost. Very good. Have a good day.